Thank you. Welcome everybody. My name is Jocelyn at Turcotte. I'm French-Canadian. I'm working at Woboq here in Berlin. I'm here today because I worked on QtWebKit and QtWebEngine at Nokia and Ninja and the Cube company. And during that time, I've been working on integrating the two compositors, the QtQuick 2 compositor and the WebKit and Chromium compositor. And in the Chromium case, we were using the scene graph, the QtQuick scene graph, to composite the layer scene in Chromium for QtWebEngine. So I'm here today to share you that experience I gained as a user of the API. So the talk today would be separated in three parts. First, we'll explain where does the scene graph come from, why is it there. The second part will be about implementing QQuickItem update pane node, basically, and use existing QSD geometry node implementations in QtQuick. And the third part is going to be about implementing your own QSD geometry node, which basically means shipping triangles and implementing your own shader in C++. So first, what about you guys? Does anybody, could you raise your hand if you ever re-implemented update pane node? Okay, and anybody here for the second part, the third part, ever fiddled with OpenGL shaders in QML shader effect or anything? Okay, so some of you guys are beasts, and if you don't know what I'm talking about, hopefully you'll have an idea at the end of this talk. If something is not clear, just feel free to interrupt me for a short question. So first, where does the scene graph come from in Qt? We can go back a bit and go back to QtQuick 1, which appeared with, I don't know, Qt 4.7, or I don't remember. And initially, it was an evolution of UI files that you have in QDesigner. So it was meant to be able to do animations and some more scripting directly in the structure of the file instead of having all the logic in C++ and everything in the UI. It was using QGraphics view for rendering along with QPainter, and it was using QScript for the scripting part. QtQuick 2 came with Qt 5. It was built directly on top of QtGUI. It was using QWindow or a subclass and QOpenGL for rendering. It's not using QGraphics view, not using QPainter. The scripting has been forked, and the windowing and event system has been forked from QGraphics view as well. If we look at the architecture of QtQuick 2, we have OpenGL on the right. You have QML components and QML engine that you probably know already about a bit. QQuick view is just a subclass of QQuick window, and the window is the surface for the rendering of everything. And in the middle, you have the QQuickItems, the built-in one that come with QtQuick, for example, QQuick rectangle, QQuick text. And the QML components are going to use those QQuickItems, and those QQuickItems are going to use scene graph nodes to define the rendering. So QQuickItem is taking care of the event system. There's no event handling in scene graph nodes. It's only there for rendering. It's a replacement for QPainter, you could say. And the scene graph nodes are going to be walked by the scene graph renderer to convert this into OpenGL commands and make this as efficient as possible. Here I'm showing something that is important, is that as you know, everything in QML is a rectangle. If you want a circle, it's really difficult. And this is because everything is, in the end, a triangle in OpenGL. You make a rectangle by using two triangles made out of 4 vertices. Now let's try to look how it's rendered in QtQuick 1 and why QtQuick 2 came to exist. So the way it used to work basically in QGraphics view is that you have a scene made of QGraphic items, and you want to render the scene back to front imperatively using paint virtual call. And this paint command, this paint virtual call is going to send paint commands basically through the QPainter abstraction. So set this brush, draw this rectangle, draw this image. And the paint engine behind the scene, for example, the raster paint engine, is going to interpret those paint commands and transfer this into changing the memory to change individual pixels. So the way it works is that you're going to paint the background, then paint the frame of the OK button, then the text, then the frame of the cancel button, then the text. And this works great. The clipping makes sure that you don't move memory that doesn't need to be updated depending on the dirty area on the screen. But the problem comes when Qt wanted to target embedded and mobile devices. So, of course, you want to use OpenGL. So, yes, let's just convert those QPrinter commands into OpenGL commands. So, yes, it's not too difficult. So you have you set up your shader, your OpenGL states to render the frame of the OK button. Then you change the state again to render the text. And this is the nasty part, is that you're going to change the state to render the frame of the cancel button to the same state it was for the OK button. And you're doing so much changing here and there that you would have been much better than rendering the 2 frames before and then the 2 texts. So some paint engines, for example, Skia is going to reorder those things and do everything. But in the end, it's basically going to reconstruct, like try to imply information that was already in the higher layer in the item tree. So this is what the scene graph does. Instead of going to an imperative abstraction, it takes the declarative abstraction of an item node tree and it's transferring it to a rendering node tree, and it's transferring all the information it needs to render the scene, to convert this essentially in the end to OpenGL commands. So you're going to have 2 geometries for the 2 frame of the button with a material associated, and the scene graph can see, okay, this is the same material. Basically, they don't overlap, nothing. So yeah, let's just render them together in one single draw call, and then you use the parallelism of the GPU much better. So let's try to see how do we convert how do we extract the information from the QQuickItem and put it in the scene graph. Let's start with a quick demo of the code first. So it's basically just a is the text big enough? Or I guess I can make this a bit bigger. No, not too much. Huh? Okay. So this is the QQML application engine that I use just to be able to use a string for my QML program for the presentation. I convert this using QtStringify just to have the syntax in the editor, but then I need to put semicolons. But anyway, what's important here is that the scene is just a rectangle. It has 2 property bindings to define the size, depending on the parent, and it has an anchor that is going to basically change the X and Y position. I'm going to use, oh, this is, okay there. I'm going to use this environment variable here, which is going to convert, to tell the scene graph to output the whole scene graph on the command, on std out, which normally you don't need to see. But in this case, what I get is my rectangle in the middle. And this was the first frame that just had the scene before the QML scene was loaded. And this is my first frame. You see the same 2 nodes that were for the beginning or for the empty scene. And here, those 2 nodes here are for my QML rectangle that you see in the scene. So the transform node contains here the X and Y position. And the geometry node has material, let's say red. And it has 0, 0, like you would do with QPrinter. You paint everything at the 0, 0 coordinate of your widget. And the height and width are converted here. Oh, sorry. And if I just resize this, then you see the scene graph tree changing on every frame. So, okay, let's see, before. Here you see that the opacity is 1. The opacity is implied. We don't see it here in the screen. So if there's nothing, no information there, it's going to be 1. But if I come here and I put opacity 0.5, and then clipping, since it works similarly, if I run this again, here you saw that before, this is the old one. Before we had the transform node, which is handled by the item, and this was our paint node, the geometry node. But if I run the new one, here you see that this was my transform node, my paint node, and now there's information that has been added in the scene tree for opacity and clip node. So the opacity node is there to set an opacity of 0.5, and it's going to affect all the children. So it's going to be cascading. So if you have multiple opacity node, they're going to basically multiply the same way that if you set opacity on a root item and then on child item, the common child of this whole chain is going to have the opacity multiplied. And this is how it's implemented on the scene graph node. Same thing for the clip node here. So now the interesting part is, how do we do this in C++? So here I have my QML rectangle. I'm going to make a myrect that is just re-implementing QQuickItem. And I'm going to register it. Put it in, I'll call it the main namespace, 1.0, and then I'll call it in QML the same way that it's called in C++. I'm going to go in my QML scene, import main, and I'm going to just change this for myrect. And then I don't have a color property on it, so I'm just going to comment this out. And if I run this, then my item is there. You can see the position updating. It still has the opacity and clip nodes that were added to the scene graph by the item, but there's nothing to render. There's no geometry node anymore. So this is because we didn't update, we didn't implement update paint node. So we want to tell this item how should it be painted. So I'm going to implement update paint node. I'll just copy paste the declaration from QQuickItem.h that you can also get from the documentation. And let me just do this here. And now update paint node needs to return a QSG node. So QSG node is the base class of everything. It's the same way that QWidget is the base class of everything. The same way that you don't need to have a paint method in QWidget, you can have a QSG node that doesn't do anything. But now what we want to do is return new QSG simple rect node. QSG simple rect node is a geometry node like we saw in the tree earlier. It's the one that comes in the public API that basically just show a color rectangle. So I'm going to have the bounding rect of the item, which is 0, 0 with the width and height. So it's basically just setting the width and height on my scene graph node, and I'm going to put it hard-coded to blue. So now I'm retaining this, and let's see what happens. Do the same thing, and it doesn't work, of course, because I forgot to set something very important that I myself have forgotten at least 3 times when I was trying to use the API. Why is the update paint node not even called? And the reason is that there's a flag you need to set on the item. If you look at the documentation of update paint node, you'll see this written, but it's easy to miss. Item has contents. And this is basically going to tell QQuickItem when update is called, please call update paint node. So now what happens? It doesn't work because it's private. Okay, here's my blue rectangle. Success? Well, not quite. Because now every time I'm calling update paint node, there's a new node that's added to its parent. And this here is not going to, the ownership is a bit complicated. And the way it works is here, this first parameter is old node. Basically, what I return from update paint node is going to be sent back to me in the next update paint node called. I'm going to explain why later, but let's just, what I could do is just delete old node here. But that means that I'm going to recreate it every time there's an animation frame. So what we want instead is to keep it. So let's say node equal old node, and if not node, so if I do this, the first time it's called is going to recreate the node, but it's not going to update it. And I can show you what happens. It's basically just that my node it doesn't get resized. Even though the width and height of the item changed, the rendering backend didn't change. I need to transfer all the information from the item that is updated by QML into the rendering tree. The same way that you would have a QPainter call that would use the new width every time that you call paint. So what I have to do is just to set the bounding rect again. To bounding, yes. setRect is a method of QSG simple rect node, so I'm going to be dirty and do a static cast here. It's okay to do this because update by node is always going to be, all node is always going to be something that yourself has created in update by node in a previous call. So whatever you return here, if you always return the same, you can assume that the structure is going to be there when you come back. It can be null because the scene graph might be completely deleted between frames because if the window is minimized, you want to destroy textures and stuff like this. So it can either be null or something you returned earlier. And if I do this, and I run it, then I have my C++ implementation. Cool, simple, but about this update by node ownership. So the reason there's this whole old node thing and return thing, why not just have a setter? The reason is that it's not the item that owns the paint tree, it's the scene graph. Your node is set in the scene graph, and the reason that it can only be owned by it is that because it's running in a separate thread. So the items live on the GUI thread, and the rendering tree, the whole thing, is living on a separate thread, which is the scene graph thread. The reason there is a scene graph thread is basically because of vsync. So the way that vsync works is that you have a back buffer and a front buffer, and you don't want to have tearing. So while you render your back buffer, after this you tell OpenGL, please put this on the front, and meanwhile you're going to render the next back buffer. But then you cannot queue buffers. Then you would be either have lag, either you would be dropping frames that you spend so much resources to compute. So the thread is blocked. If you have two back buffers in a row, your thread is going to block, which happens all the time if you have a simple scene. So that means that if you do this on the GUI thread, you're going to block the GUI thread. If you have a lapse of 16 milliseconds to render the whole scene, and you have a simple scene, then you're going to wait for 10 milliseconds in that scene. So that means that you always have a latency of at least 10 milliseconds to handle events or send network requests or stuff like this. So the solution is to put everything in a separate thread. So like we see at the bottom here, the scene graph is going to wait for vsync, while the GUI thread can go back and handle events and do useful stuff. So, and in general, the way that the classes are separated is that QQuick classes live in the GUI thread and QSG classes live in the scene graph thread, even though both of them are in the QtQuick module. Now, the tasty part is that update paint node is the portal between the two threads. You don't need to use mutexes. You shouldn't use mutexes. There's no event loop on the scene graph thread. You have to take update by node as something that it's like a door that opens. You shuffle every information that you have from the item that you accumulated. This needs to be rendered. You commit this to the scene graph thread only in that call. And the way it works is just that there's a synchronization mechanism in QQuick window and the QSG render loop that when you start updating the nodes, the GUI thread is going to be blocked. And this is going to run on the scene graph thread, just so you know. So creating Q objects in that thread is going to be messy. Please don't try to do this. So you can do anything you want. This is why I could call a bounding rect earlier on my QQuickItem, even though I was in the scene graph thread, because at this moment, you know the GUI thread is blocked. I'm going to show, I call it pathological because I didn't try to make it fast, but let's have a look at this. So let's pretend that our boss asked us to do a QR code animated for some advertising panel or something. So the animation here, I control from 0 to 1 using the slider manually, is that it's going to move dots based on the arbitrary logic that I choose, that it counts the number of dots around, so it crumbles. Basically, the stuff alone crumbles first, and the other one crumbles later. So if I animate it, it looks like this. And this is all done in QML, but the information comes from C++. I use libqr encode to be able to fetch that information from C++, which is a C library, but anyway. And then I put this information back to QML, and I create a QML rectangle for each of those single black nodes here. And then I animate the position and the opacity of those QML rectangle in QML. Let's have a look at the code. So the code is just a QQuick view with a main.qml, and here's my backend. I register, it's a Q object that I register to be able to instantiate it in QML. It's the same as if I was doing, for example, a global set context property on the QML engine. This engine, this backend is basically, like I said, a Q object, and it has a single static invocable just to be able to call it from QML. And what it does is that it's going to convert text, a URL in this case, into a Q variant containing a Q gadget. I mean, it could be a Q object, but then you need to create it on the heap and everything. So it's just a struct Q gadget that I put a Q variant in a Q variant, which contains itself a Q variant list of Q gadget. So in the end, this is the information that's important to us. What's the X, Y position of every on those QML rectangle that we want? And what is surround count is that property that I feed back to QML that counts the number of points around. So I'm going to decide based on this surround count, should this point move first or should this one move first? That's not the point of the presentation, but we'll need to carry this information around for the whole talk. So this part is just, let's call it business logic. The implementation is just calling libqr encode, and it's taking the data structure of libqr encode, counting the surround count, and in the end it just happens this is my Q gadget that I append in the Q variant list. This is just the backend. We won't work with this piece of code until the end. This is my main.qml file. The important part is here. It's my QR code QML code, which was basically the whole QR code in the middle. It has my text property that is static and a review progress property that I'm animating. I said to the slider to be able to set it manually, but this is the animated value that goes from 0 to 1. Everything around is just to have, I'll have a little benchmark that I'll show later to have multiple codes on the screen. And the important part is here. This is my QR code. This is what we'll be working with. So here's my text and my reveal progress property. Here's my C++ backend object that I instantiate because I registered it. And here I have a property binding that convert my text into my Q gadget, wrapped in the Q variant, in the property var, etc. So I have a white rectangle that is the parent of everything you see here. And here is where it all happens. So my list, my Q variant list is used as a model to, in the end, get my rectangles on the screen. So each of those dots, because of the repeater, is going to be converted to a rectangle. And in this rectangle, I'm using model data, which is this individual dot. And I'm going to position this on my background, X, Y, all of them, depending on the information I got from C++. The coordinate system of this X and Y is each point is 1 unit. So I don't want to have a QR code of 1 pixel per point, so I'm scaling it back a bit higher here. So I do, this is the width of my QR code, and then I'm going to scale it just to have the geometries, the rectangle, triangles being scaled in the end. So anyway, here's the animation. This is animated from the slider, which eventually goes in my item, and this here is going to create is a property binding that's going to trigger this dot progress, which is a value from 0 to 1, that is going to animate each of the dots. Should I move now, or should I move when the slider is further down? And this is a bit of logic that I have here that just takes the surround count into account, which is the value, taking some stuff. We don't need to go into details into this, but what's important is that I'm using this value to, in the end, set the opacity and a Y offset on my rectangle. So I'm showing you this, and it's fast. I mean, why am I coming with this? If I look at, I guess you don't see the FPS so well. Yeah. So it's 60 FPS. Yeah, sure. What's the problem? So if I put 4 of them, it's still 60 FPS mostly. but this is where it gets messy. So I just have, I mean, it didn't scale at all. I just put 16 of them, which could be just one big QR code with a long URL like some people like to use sometimes. And it would just be horribly slow. Why is that? So if I look at the CPU usage for this, there I am, using 100% CPU trying to render something. I mean, QtQuick is supposed to be quick. So what's the problem? Anybody has an idea? Okay, I'll tell you. The problem, actually I didn't know myself. I had to profile the code, which is the right thing to do anyway. The problem is the property binding. I mean, I had this huge property binding that was using cosine function and stuff like this, and I put this in JavaScript, and it's fine to do this, but in this case, is that for each animation frame, for each of those single dots on the screen, I have to execute those three property bindings, the main.progress and the opacity and y1. And if you run this in instruments or perf, you're going to see just the property bindings being executed. So let's try to see what happens where I animate those properties. Where I animate opacity and y, to come back to our scene graph case, update is going to be called on the item, and the item itself is going to update the transform node that we saw earlier in the dump, and the opacity node that I had, and it's going to add the offset to the transform node, and it's going to update the opacity node. And this, in the end, is going to affect rendering. So this is the question. Do we have to use QML in this case? I mean, QML is the bottleneck. Sometimes you can't avoid it. But in this case, well, to be honest, I chose the design because I could do it. Else I would be in trouble here. But you don't need direct control on each point. You don't have any event handler. It's just pure rendering. It's just like, let's move this thing there the same way that you just put this thing in a QPrinter call. And on top of this, the points originally come from C++. I took this information from C++. I move it in a QGadget crazy technique just to bring it to QML. And this, in the end, is going to be reconverted to essentially geometry nodes. So what I can do in this case is that I can just use the text property and the reveal progress property that I had on my QML component and basically convert my QML component into a QQuickItem. So instead of having a QML component with a bunch of child items, I'm going to have one item that is going to have a bunch of child nodes. So this is the plan here. We have one item, and sorry for the drawing. We have a white background in this case, and we'll have one geometry node for each of the dots. And this is our paint node tree. This is for one item. This is the paint node tree that we'll use. And we're going to create manually this transform node and opacity node. We're going to build a tree to match what essentially a tree of item would have done, but we'll do it confined into one item. So I'm going to set the geometry itself is going to be moved in the coordinate system of the item instead of being to its own rectangle. And they're going to be positioned directly where they should be. And I'm going to use the transform node only for the offset. So the transform node is going to be an identity matrix when the code doesn't animate. But as I move the code, it's going to be plus 1, 2, 3, 4 dots. And I'll do the same for the opacity node that is a parent of my geometry node here. So let's try to do this. Okay, let's go back to main.cpp. No, actually I should maybe get the code first. So here's my main. I have my QR code item that replaces my QR code helper. And the rest is the same. Here is all the same too, but here, where I had the QR code helper with a single QR code data invocable, now it's a static private that I'm going to use internally. And here are my two properties that basically reflects what I had in my QML component originally. So each time I'm going to call the setter, I'm going to call update. and I'm going in update by node to do the logic that's interesting to us now. So let me go into update by node, or first the setters. So a basic QQuickItem setter, you keep the value that QML sends you into a member variable, you emit a signal for the property to update any property binding on this value, and here I'm setting text dirty because if the review progress property changed, I don't want to recreate my QR code. So I'm going to track, did the text change actually since the last update? And I'm going to call update. Same thing for review progress. And here our update by node is basically a more complicated version than the one we had in the simple case at the beginning. So I'm going to have my background node here as basically just a simple rec node as well. And I'm going to put everything in an empty QSG node. So here I'm doing the static cast the same way that I did earlier, but now I'm starting to assume stuff from the structure of the tree itself and not just the type of the root. So the background node and the dot container. Here I'm deleting all the nodes that were there before because, sorry, the text changed here. So let's delete everything, every single chain that was there. We're going to recreate them, but I keep the basic structure. I just change the content. And here I'm doing the get QR code data that I was doing in QML. It's basically the same code. I'm taking the text value, taking the code that contains the dots in it. And for each of those dots, I'm going to create a management QR code. You can do it directly in update by node if you want, have a for loop with 6 embedded stuff. But in this case, I'm just going to have a class that implements the logic that I'm going to create later. So here is the animation. Each of those dots that I created here is going to have a set review progress, and I'm going to set the review progress. So if I have 200 dots on the screen, for all of them, I'm going to set the animation value. So if I look at the top, then like I said, I create the chain of all my nodes. So the translate node is a child of the management node, opacity node, a child of the translate, geometry node, a child of the opacity node. That is in the end a simple rec node that we had earlier. I'm putting it red this time. And the animation here says review progress. It's basically the dot progress property binding I had earlier. I even have a variable as the same name. And in the end, what I'm doing is I'm setting the opacity and the matrix of the translate node manually. Translate node is a matrix. You have to do everything. You can do scaling with it. You can do perspective. But in this case, I'm just using a translation. So looks the same. Let's just put it in the profiler just to see the frame rate. So if I animate it the same way as before, and I do this, then my 16 node works almost at 60 FPS. You see in the middle, it's like, ugh. So let's put more. Okay, now it's really nasty. What's happening there? So the problem in this case is actually further down the rendering path. We got rid of the QML property bindings bottleneck, but in this case we just hit a scaling issue a bit further down the road because it's just a big scene. I mean, it has a lot of stuff on it. So the problem is batching, and the way that batching is used is for flickable, for example. There's a thing in OpenGL, which is a draw call. Usually you want to group stuff together. So if you send one triangle, then the GPU goes like this, and it has to set up, okay, change the uniform and change the state. So if you put everything in one single draw call, it's just more work, and you can just do more stuff. The same way that when you paint with a roll, you don't want to start painting the corners with it. You want to have enough surface to render. So by batching stuff together, you're just making sure the GPU can be more efficient. And in this case, in the flickable case, that's perfect. You have a flickable that moves. You have a bunch of text that you want to be grouped together. You don't want to render every single glyph separately. So you're going to batch everything together, and when it's time to animate, you just animate the transform, and everything is in 2-3 draw calls. It's just great. But in this case, is that we trigger a reconstruction of the batch, because the way that transparent node have to be done, you cannot have overlapping nodes in the same batch, because you don't know at which order they will be rendered, and you don't get the same value if you have a transparent image on top of a white background or a transparent background on top of an image. So you need to make sure that the batches are in order. And in this case, since the rectangle are moving, then the batches algorithm always have to reorder everything. So anyway, what we want to do in this case is, I forgot to show you the CPU usage, but I was still at 100 CPU. So in this case, we have 2 CPU. In this case, we have the CPU doing all the work, is doing all the transform, while in the end, the GPU is sitting there and saying, okay, when's the next frame coming? I can render this in a tenth of the time you're doing, and the CPU is still doing this. So what we want is move all this computation on the GPU. So this brings us to the second part. Let's try to make triangles ourselves, and let's try to animate this directly in the GPU. Before you start doing this, I mean, it's tempting. Okay, maybe. Okay, so before we do this, you can have alternatives. So the shader effect is basically a fragment shader, and the painted item and the KML canvas can also use the GPU, and the QQuick frame buffer object can also be used to render standard OpenGL code. So this you can see Gracip's talk right after this that is going to go more into depth. But what we want first is to implement our own geometry node. So a geometry node is going to need 2 things: a geometry, which is a bunch of triangles and attribute, and a material, which is going to be a bunch of variables that are going to control the whole rendering. In our case, we're going to have each of our point as 2 triangles to be a square, and we're going to put the surround count as a property of this to be used in the vertex shader. And we're going to pass the reveal progress as a uniform so that the vertex shader can use it. It's going to be the same value for the whole set of points. The QSG material shader is instantiated by the QSG material. There's only one instance for everything. It's going to be used to control the lifetime of the shader itself. So what we want is basically this. We want to do the y plus equal and the opacity logic directly on the GPU. This is what we want. So to do this, we need inputs, and those inputs are going to come, like I said earlier, from the vertices themselves. So in this case, I'm going to have 40 vertices. I'm going to put the surround count in it. I'm going to use this value in the vertex shader. Another thing is that we won't have that many geometry nodes anymore. We're going to do our own batching ourselves in one geometry node. It's not necessarily a geometry at this point because they're going to be separated, but in the end, the QSG geometry is just a bunch of vertices grouped in triangles. So there's a way to just put everything in the same QSG geometry. Oops. So the other demo, okay. What changed in this case is only QR code.cpp. So we have the same thing as basically we had before with the QQuickItem. Everything around is the same. The interface from QML doesn't change. What changed is what do we do in update paint node. I'm first going to show the fragment shader. I mean, I don't want to go into details, and it's still a string that I convert to QStringify so that the GPU driver can convert this and compile it. Well, what's interesting is those here. The position comes from my QSG geometry, the same as the surround count. So I pass them to the QSG geometry, and the reveal progress property that is animated is going to be used to move stuff around is passed as well. Again, this is the same logic with the dot progress that I ported first from QML, then to C++, then to a shader, and it's going to change the Y the same way as before. It's going to move it down, and it's going to change the opacity. It's changing the opacity by a varying that has first to go through the fragment shader, which is then going to be set as the color. Let's go down to the, oh no, sorry. So if I go a bit further, we're going to see the QR code material. So the QR code material, if I go a bit further, is the data. It contains the data of the material. Is it red or is it blue? And the material has to send to the QSG material shader, which is the code how to do this. Here's the information to do your work. Here's the texture ID to do it. Here's the color. And I'm going to transfer this in update state, which is a method of the material shader, which takes the material. And here, I'm basically just call it could be just a plain OpenGL call. This is a QOpenGL a shader program class that essentially just call OpenGL to set the value of my animation directly in OpenGL. So this value here was initially in QML, which first transferred it in the QQuickItem, then it got transferred. We're going to transfer it in update pane node into the material, and the material itself push it into the GPU. So there's a whole queue of things to put this stuff on the screen in the end. And if I go in update pane node, this here changed because now I only have one geometry node. I can put this in my static declaration. I don't have a tree of geometry node anymore. I'm just going to change the geometry on the geometry node. And this one is not a simple rect node. It's a parent class. It's a QSG geometry node. I'm doing the same here, static cast of more or less my static structure. And here is where this is my material that I set, here on the geometry node. And I set the own material so that I don't have to delete it manually, because you want to attach everything to the scene graph, including texture, so that when the graph is destroyed, if the window is minimized, everything has to go with, else there's no point destroying it if it leaks resources. So anyway, my material, I'm going here to convert. I'm in update pane node. I take the value that came from QML, putting it in the material that the same way that we saw earlier is going to be put in OpenGL. And for the geometry case, this is the same code as before. In this case, I'm building a geometry. Oh, this is not the right one. Oh, it's okay. I'm using a geometry. Here I'm using an index buffer as well, but you could use just plain triangles, and I'm setting the geometry on the geometry node. This geometry is GL triangles because the default is just going to put all the triangles in one strip. In my case, I want to have separate one. I could use the general triangles if you know what this is, but don't worry for now. And this is where it's nasty. This is why nobody uses the scene graph API. This reinterpret kits here. So you have to write raw data into the buffer. So if I go back up a bit, here, my geometry, I set a set of attribute that you can read the code. I'll put it on GitHub later. But this attribute defines the memory model of this buffer. And here, I'm doing a reinterpret cast of a C++ structure that has the same memory layout. And I'm going to write into my buffer using basic array. I'm going to construct the C++ struct directly in memory to basically rewrite my tree float directly in it. In this case, I'm setting my 4 corners, and I'm using the index buffer to bind those corners into 2 different triangles. Any question now? Yes?
Why are triangles faster for the GPU?
A triangle is basically, like you call it a shader, but it's a shader because normally you would shade a surface with it, and because of lighting, because you want the shading on it. But in our case, we have a flat structure, and we don't have lights, I mean, in our OpenGL. So let's just call it a programmable surface. So a triangle is a programmable surface. The vertex shader is going to position the surface, and the fragment shader is going to decide what to put the color on top. So it's not faster, it's just the way that you let OpenGL render this thing like a printer, a programmable stamp or something. It's really like, there, here's your colors.
What is the owned material flag that you said?
Yeah?
Up above you said owned material.
Yeah, here. Yeah, it's because you could have, the tree is there, okay? You have the root from update pane node, and this root is transferred in ownership to the scene graph. And then the scene graph at some point can decide, I'm just going to cut this, I need the resources. So if your material is not attached to this root in any way, then it leaks. So owned material is just a way to avoid you from having to subclass this thing and put it as a member variable. It's just a flag to say, okay, take ownership of it. You could have it as a member variable if you prefer. Yes?
If all the progress is going to be the same, is there a reason why we're not just splitting the
I'm sorry, could you repeat?
So right now you're rendering each one as a it's still vertex shaded. It's processing it for multiple ones. But if they're all going to be the same, why not just render either you render to a texture and use that essentially to use the pixel shader to write everything out.
Yes, but then you would need to modify the pixels. I mean, of course, you can do the logic in the pixel shader if it's better.
Just to transform that into
Yes, of course. But then you, in this case, I wanted the hard edge, you know, like this is black, this is white. I don't want to have filtering that sometimes you get with textures. I mean, I'm here to show the pipeline, and if you have a more efficient way to do it, I mean, some guys in here are much better OpenGL programmers than I am. But the basic is that you have to carry this information from the QML down to the GPU in some way. And once you're there, I mean, you can do all the way you want. I mean, okay, so let's just see what we gain from it. So it's the same as before. Let me put it in the GPU, in the profiler. So let's go to 64 like we had before. So we get 60 FPS, 266, still 60 FPS. And now it recreates all the items itself. I'm starting to hitting the bottlenecks of QML again. And now we're back to the frame rate with 16,000 of them that we had with 16 of them at the beginning. So in this case, the GPU is still used, the CPU is still used a lot. I mean, of course, we won't display 16,000 of them. But if I go to something more reasonable, and I look, I mean, it's reasonable. If I go back to my 16 originally, you get CPU usage of, instead of 100% CPU, you get 12% CPU, because now the GPU is doing all the work. And not just that, it's also that by modifying something at the higher layer, you have to basically update all the layers under, but now since we're rendering on the GPU and computing on the GPU, then you don't have to carry this information anymore. In this case, in all frames of the animation, the whole scene graph doesn't change. It's all the same. So we just basically change this one reveal progress property that we carry down the chain to end up in a OpenGL uniform. And that's the only thing you have to do to update your animation. Yes?
What's the point of using QML here? You just prove that plain OpenGL is much faster.
Okay, yes, okay, I see. So your question is, why wouldn't I write this as OpenGL directly in basically a QQuick frame buffer object? Yeah, and the reason is that first you have the scene graph. If you want to do something efficient in OpenGL, I mean, of course, if you have an engine, use it. I mean, but in this case, you already have an engine that's already optimized and do stuff the way. So it's not so much effort compared to starting using Augur or something like this. And the other advantage is that if you use a QQuick frame buffer object, you're still going to go through a temporary texture. I mean, you still have to do 2 passes to be able to update it. And of course, on my laptop, I won't see a difference. But if you run this on the Mali 400 or something, I mean, you're going to see a performance hit. So this thing is rendered directly with the rest of the scene. So that's mainly the main advantage. Let me just finish my slides. Okay. So if it doesn't work, there's 2 documentation pages for the scene graph. QtQuick scene graph renderer is going into details on stuff, but this probably won't be enough. You'll be, why is it doing this? So go read the code. Go read the code. Use the scene graph as a framework at this level, like you said. I mean, it's just a tool for you to render on OpenGL efficiently, and OpenGL is the platform at this point. And if you want to start looking at the code, look at QQuick window, QSG threaded render loop, and QSG batch renderer. The last one, QSG batch renderer, is where all the batching is done. All the OpenGL calls are. If you want to look at something, please look at this. If you have a problem, feel free to ask Woboq. We like to deal with this kind of code, and maybe we can help you find a better solution or to change your design. So conclusion, QML property bindings are convenient but have a limited scalability. Using too many QSG geometry node can also be a scalability issue because of batching, and I mean it has to walk the structure. And I didn't show you, but the red one that I was moving that was really dependent on batching, if you just disable the opacity node, you get double the performance. So blending has a cost, so make sure that you don't use transparent geometries unless necessary. And at the end, I just say that if you compute on the vertex or fragment shader, you can get like 100 times performance just because the GPUs are faster, especially on embedded. So for example, the Raspberry Pi, the theoretical gigaflop that you have on the GPU versus the CPU is 150 times more, the first one. It's just some embedded devices, you are advantaged to use the GPU. Thank you.